This video is to do with annuities, and the exercise in your textbook that it is related to is exercise 9E. So an annuity is just a type of investment. With this type of investment, a person invests their money in an annuity. They put it in the bank, for example, and it earns interest. Okay, so the money grows a little bit, and then the person takes a regular payment from that annuity until the balance reduces down to zero. So in real life, I guess a lot of older people, when they retire, they tend to put their money into an annuity, and the annuity sort of pays them similar to their wages when they were working. So it sort of gives them that regular idea of a payment, sort of a way of sort of budgeting their money. So the maths that's involved in an annuity is exactly the same as the maths involved in a reducing balance loan, except the money is going in the opposite direction. Okay, so if you'll remember back to the start of the chapter where we started talking about reducing balance loans, that is where a person would borrow a lump sum of money from the bank, and the bank then charges interest on that amount, so that the amount owing actually grows bigger, and then the person makes payments back to the bank in order to reduce the balance down to zero. So in the annuity, it's just the opposite direction. So it's the person putting their money in the bank rather than borrowing, and then the bank paying them a little payment every month or every quarter, whenever, instead of the person paying back the bank. The idea in both of these situations is to reduce the eventual balance down to zero. Okay, so it's basically a way of a person investing a sum of money and then using it at a sort of controllable rate. Okay, so the model for the annuity looks exactly the same as the model for the reducing balance loan. And as I said before, the direction of the money is the only difference. So instead of taking money from the bank, we're putting money in the bank this time. So as we flick through the booklet, you'll see there's a couple of examples, and so I'll take you through a couple of the examples first and then let you set to work on exercise 9E. So in this example 11, you can see there this person, Reza, plans to travel overseas for 6 months. So what he's doing with this investment, he's investing $12,000 in an annuity, and while the money's in the annuity, it is earning interest at a rate of 6% per annum, and then he's taking a monthly income or a monthly payment of $2,035 per month for a 6-month period while he's on holidays. So rather than spending his entire allowance of $12,000 in the first month while he's overseas, this is a sort of a way that he can control that or budget that income and try and make it last for 6 months. So modelling that annuity using a recurrence relation is nothing new to you. So V0 is still the principal, and then Vn plus 1 is going to be big R times Vn, the interest rate, times Vn, take away D, which is a payment. Okay, so we basically have to figure out what the value of the payment is, what the value of big R is, and the value of V0 as always. So from the story, we can see that he invests $12,000. So V0 is $12,000. The interest rate is 6% per annum. But we are seeing in that story there that he's taking a monthly income, so we need to calculate a monthly interest rate accordingly. So the big R value is going to be 1 plus 6% divided by 12, and that gives us a decimal R value of 1.005. Okay, the D value or the payment value there is $2,035. And then if we're going to write that recursion relation there, using those values that we've just calculated, Vn plus 1 is going to be 1.005 times Vn. So that's the bit that grows the annuity, the 0.5% interest. And the minus $2,035 is the payment that he's taking out monthly. Okay, So then example 12 then moves into a bit of questioning about that actual recursion relation. So they give us there the same one we've just written up above. So V0 being 12,000, Vn plus 1 is 1.005 times Vn minus $2,035. So this one here, it's telling us that the value of the annuity, that N in that case, is after N payments, so N months. Okay, so when you're using your calculator with recursion in these examples, we're starting with 12,000, we're hitting enter, we're multiplying by 1.005 and subtracting 2035. Then hit enter 6 times for 6 months of payments. And you can see that the first question asks you use your calculator to determine recursively. So that's how you know you have to show calculations in every value from V1 to V3 there. So recursively, you need to find the value after 3 payments has been received from that annuity. So after 3 payments, you can see there that the value of the annuity is $6,045.33 left. So then he continues on his trip, taking out 3 more monthly payments. And you can see there part B asks you, is the annuity fully paid out after 6 monthly payments have been made? And because you can see there that it's not down to 0 yet, there's still 88 cents left in that annuity. So the last payment would be more than $2,035. Okay, so that 6th payment in the last month, he would take out the $2,035 plus that extra 88 cents that's left in there, and that ensures then the annuity is fully paid out and the value of the annuity now is 0. Okay, if we flip over, you'll see there's a couple of pages in your booklet on amortization tables for annuities, and I'm going to come back to that in a moment in a different video. So I'm just going to keep flipping until we get to page 22, because I want to actually take you through using the solver with an annuity. So we've done the solver before with a reducing balance loan, and you'll hopefully remember that I sort of highlighted this section here on the rules page and said that was a really important part with a reducing balance loan. Well, it's actually a really important part with the annuity as well. So thinking about the direction the money is going when you're investing money. So the PV is always going to be negative because you're investing, you're putting money away from you, you're putting the money into the bank, so negative PV. Because the payment is coming this time to you rather than away from you, the payment's coming to you, the payment will be positive. And the future value, because it's your money that's being talked about, or Reese's money or Joe's money, whoever's money we're talking about, it's their money. So the money is always going to be either, in the future value, always either going to be positive or 0. Okay, you're never going to have to pay more into the future value. The future value is owed to you, basically. It's your money. So really important to remember those couple of direction signs. So PV always negative, payment always positive in an annuity, and future value either positive or 0, never going to be negative. Okay, so if we have a look at the sort of example that is shown in exercise 9E, example 13 is a perfect example. So a little story about Joe investing $200,000 into an annuity and paying 5% compounding interest per annum, and it's compounding monthly. So that gives us a bit of information for our solver. He wishes to be paid monthly payments for 10 years. How much will he receive each month? So we need to have our payment window empty to figure out how much is going to be paid. Obviously 10 years of monthly payments is going to be 10 times 12 in the N window. The interest rate's 5% compounding monthly. So the PPY, CPY both 12. The PV, the investment, is $200,000. And because Joe's putting the money into an investment account, it's going away from him for the time being. So the sign on the 200,000 is negative. And the idea is for Joe to use all the money and end up with the future value being 0. And when you put that into your calculator, hopefully you will see that his monthly payment for the next 10 years would be $2,121.31. Then they ask you, okay, well, if he doesn't want to receive $2,121.31, he wants to receive a payment of $3,000 per month. How long would that last him? So over on the right-hand side there, you can see the calculation for part 2. Still the same interest rate, the same PV, the same FV. He's going to use it all up again, and it's still compounding monthly. So everything's the same, except the payment is $3,000 this time, because he wants to see how long that will last. And the N will be the one that's the blank window this time. So in that case, 78.26 and so on, in that blank window will tell us that that annuity would last Joe $3,000 a month for 78 months. Okay, that 78th payment would be slightly larger than the $3,000. You can tell that by the 0.26 on the end. So it might be another $700 or something extra on that last payment. So the 78 payments won't completely get the value down to 0, but that last payment would be adjusted. And part 3 on that question there asks you, what would the interest rate be, rounded off to 1 decimal place, if he wants to withdraw $2,500 as a payment for 10 years. So again, it's giving us enough information there to be able to fill in all of the windows. $2,500 in the payment, 10 times 12 payments, 10 years of 12 payments in the N window this time, and the only window blank this time would be the I for the interest rate. And when you round that interest rate to 1 decimal place, to make that work for him for 10 years, getting $2,500 a month for 10 years, the interest rate would have to be calculated at 8.7% per annum. So hopefully that gives you a little bit of an insight into annuities. The exercise that goes with that sort of idea, that sort of theory there, is exercise 9E. So I'm setting you 9E as an exercise to have a go at, and obviously am looking for questions and any issues that arise from that exercise. So I'll make another video that shows the amortization table for the annuity and how that works, but I think the solver is the go for exercise 9E.